Day 144, Part B, Simplifying Resistor Circuits. Once again, diagrams will be very important here, and practice is very important. You look within this complex circuit to where the simplified parallel and series portions are. Once again, practice. Here I see, hopefully you'll see, that the 6 and the 12 on the far right are in parallel with each other. If you were to look at this location right here, this little spot right here, let's just call that point A, and let's call the spot right down here point B. There are two ways to get from point A to point B. You can go through the 6 ohm resistor or the 12 ohm resistor. They are in parallel with each other. So I'll do the computation over here. We have 1 over our total will be equal to 1 over the 6.0 plus 1 over the 12. You go to your calculator. The combined resistance of those two resistors is 4.0 ohms. So now we'll redraw the diagram. So here's the new diagram. I've replaced the 6 and the 12 ohm resistors with its equivalent resistance of 4.0 ohms. I've also labeled on the far left over there the given 0.5 ohm resistor that was stated in the problem above. Alright, next step. The 4 and the 2 ohm resistor on the far right are in series. And that's an easy combination because you just add those. 4 plus 2 is 6. So I'll draw that new diagram. So the 6.0 ohm resistor replaces the 4 and the 2. Hopefully you're starting to see a pattern here now. If I look at this point over here, call it point D and point E, between those 2 points there are 2 pathways, the 3 and the 6 ohm resistors. They're in parallel. So I'll combine them by the parallel rule. I'll do the math up here to the right. So that'll be 1 over the combined, our total will be equal to 1 over 3.0 plus 1 over 6.0. If you do the math there, the total combined resistance is 2.0 ohms. So we'll draw a new diagram. I'll do that on the next page. So the new resistor is 2.0 ohms, replacing the 3 and the 6. It bears repeating at this point, once again, when you have 2 resistors in parallel that are combined, or any 3 or 4, the combined resistance is always less than any of the given resistors, simply because multiple pathways result in a low overall resistance, because it's like having more roads from point A to point B or point C to point D. The overall resistance is less than any of the individual resistors. Now, this basically is a one-step problem to finish it off, because we have a single loop here now with 4 resistors in series. There are no multiple pathways, so it's simple addition. Just add the 4 plus the 2 plus the 1 plus the 0.5. The total overall resistance will be 7.5 ohms. So let's draw that. We've finished our first goal, and that is to find the overall equivalent resistance. So our answer is 7.5 ohms of total overall resistance in this circuit. Let's find the current. So V equals IR. We have 8 volts, 8.0. Current times the 7.5 ohms of resistance. The current in this particular circuit comes out to be 1.1 amps. Now, one way we show that in a diagram is by arrows like this. This shows the flow of current. Typically we'll draw this neither clockwise nor counterclockwise, but what we usually do is we start with the positive part of the battery. That's the long line here with this symbol is the positive side, the short side is the negative side. We usually draw these arrows from positive to negative. That shows that the current is flowing that way. Now, once again, the current does not start at the battery. It all starts up all at one time, but when you draw an arrow, you got to start at some place, and we usually start at the battery. But there's a flow here of 1.1 amps. Let's also do the power of this circuit. It didn't say to do that, but we're going to do that. What kind of power is supplied to this particular resistor, whether it's a light bulb or a carbon fixed resistor. And we have a couple of options, but the one that I generally like to use is P equals I squared R. So we have, in this case, for that particular resistor, 1.1 squared times 7.5 ohms power equals 9.1 watts. Alright, so that's simplifying a circuit, following all our rules of combinations for parallel and series resistors, finding the overall current and the overall power of this particular setup. And what we're also going to do here, since we can, is we're going to find the power used by each of the actual individual resistors in the actual circuit. And the way you do this is you got to work backwards from this particular simplified diagram at the end to the one before it, at the one at the top of this page. For example, in this top circuit with the 0.5, the 4.0, and the 2.0 and the 1.0 ohm resistor, we know that there's a flow of current. It's a single loop, and that flow of current there is the 1.1 amps. So I know that each of these resistors has 1.1 amp of current. So there's 1.1 amp of current through this resistor, 1.1 amp, and 1.1 amp. What I also would like you to do, in addition to finding the power, is to find the actual voltage of each resistor. Now, I'm not going to show you the work for all these because basically what we'll be doing in every case here is V equals IR, and a lot of these we can do in our head, or we're going to do P equals I squared R, and then just write down the result. For example, going to the 0.5 ohm resistor, the resistance is 0.5, the current is 1.1, so if we multiply 1.1 times the 0.5, we find that the voltage of that particular resistor is 0.55 volts. And then 1.1 times 4.0 for this 4.0 ohm resistor, that gives you 4.4 volts. This resistor over here would be 2.2 volts, and this resistor right here will be 1.1 volts. So I find the voltage of each of those resistors, and a check here would be to take all those black numbers I just wrote down, the 1.1 plus 2.2 plus 4.4 plus the 0.55, that should come out to be 8.0. It actually comes out a little high because the 1.1 amp is rounded up a little bit from 3 sig figs to 2 sig figs, but it comes out to be like 8.2 volts. They need to add up. The voltages in a loop need to add up to the battery voltage, and I'll explain that more in a future lecture. Anyways, those are the voltages of those four resistors, but their power is just I squared R. I'll do that off to the side and then write the answer by each of those, or actually I'll write the answer out here. In other words, the power for the 0.5 ohm resistor will be 1.1, it's I squared, times 0.5 will give you some power in watts. The power for the 4 ohm resistor will be 1.1 squared times 4. The power, so each of these, for the 2 ohm resistor, 1.1 squared times 2, so it'll be half of the 4 ohm resistor, and the power of the 1 ohm resistor will be 1.1 squared times 1. Let me do those and write them in. So the 0.5 ohm resistor, it comes out to be 0.6 watts. So the 1 ohm resistor will be just twice that. It's 1.2 watts. 2 ohm resistor will be twice the 1.2, so it'll be 2.4 watts. and so on and so forth. The 4 ohm resistor is 4.8 watts. So that's the power of each of those four. 3 of them are actual resistors. The 2.0 ohm resistor is a replacement resistor. So we'll go back to the previous page, but we do need to keep track of these 3 numbers right here going to the next page. It's a 2 ohm resistor, 1.1 amps, and 2.2 volts. So let's go to the next page. What I've actually done here is gone back to the previous page, and the 3.0 ohm resistor and the 6.0 ohm resistor in this bottom diagram were replaced by the 2 ohm resistor, and the 3 and the 6 are in parallel. The 2 is the replacement. The important thing here, and this is the key idea, is that when you're in parallel, the 2 resistors have the same voltage, and I believe the voltage was 2.2 volts. 2.2 volts for each of those resistors. They have different currents. In fact, the 3 ohm resistor will have twice the current as the 6 ohm resistor because it has half the resistance. But if you want to check that, you just use V equals IR, and I'll write it down this one time for each of those. V equals IR, where V is 2.2, I is unknown. The sum of the current is going to be 1.1 amps. We'll see that in a second here, times 6. So we calculate the current through the 6 ohm resistor, and we calculate the current through the 3 ohm resistor the same way. And the results are, for the 6 ohm resistor, we get 0.37 amps. I is 0.37 amps. And for the 3 ohm resistor, it's twice that basically, it's 0.74 amps. I'm going to write that down. This is, I'll use a different color. This particular resistor, the 6 ohm resistor, has 0.37 amps of current, and the 3 ohm resistor has twice that. It has 0.74 amps. And you can verify that using V equals IR. But the other interesting thing you can do is add the 0.74 and the 0.37, and lo and behold, you do get 1.1 amps. In other words, the sum of those two currents equals the total current through its replacement resistor. We'll talk more about that later. All right, so now we've got to keep working backwards. Oh, we were supposed to find the power as well. So we really don't need the power of the 6 ohm resistor. What we really need is the power of the 3 ohm resistor. And I'm just going to use I squared R. So you take your 0.74 squared, multiply it by the 3 ohms, and you get 1.6 watts. So the power for the 3 ohm resistor was 1.6 watts when I calculated I squared R. All right, keep going backwards here. We're going to transition from the 6 ohm resistor to its pair, or the combined 4 and 2. And once again, when you have 2 in series, the 2 in series, the 4 and the 2 in series have the same current as each other, but they have the same current as its replacement resistor, which is the 0.37 amps. So I'm going to write that down. We have 0.37 amps through each of those resistors, because the flow is the same. So I can calculate the voltage by just taking the resistance times the current. Now you'll start to see patterns here. So I'll calculate the voltage that way. They're each going to have a different voltage, and I know if you have twice the resistance for the same current, the 4 ohm resistor will have twice the voltage. But let me calculate those. Actually, 2 times 0.37 gives you 0.74 volts for this one. Excuse me. And then the 4 ohm resistor will have 1.48 volts. You could round that off if you would like, but 1.48 volts of electric potential difference, voltage. If you add the 1.48 volts plus the 0.74 volts, you should end up with 2.2 volts, which indeed you do, because the voltages in series add up to the total voltage. But I now want the power for each of these. Actually, the only one I really need to worry about is the 2 ohm resistor at the bottom. I want the power for that resistor. it's just going to be the current, which is 0.37 amps squared, I squared times R, so 0.37 squared times 2, I squared R, gives you 0.3, I'm just rounding off to 1 sig fig now for reasons you'll see here in a minute, 0.3 watts. I'm rounding off all my powers to the tenths place. You can say 0.27 if you would like, if you want 2 sig figs there, but we don't really need to do that right now. We'll come back to that. All right, we have one step left. We have our 4 ohm resistor, which had been replaced, was a replacement for the 6 and the 12. Once again, the 6 and the 12 are in parallel. They have the same voltage as each other, different currents, but their voltage is the same as the voltage for the 4 ohm resistor, which replaced it. So it's 1.48 amps, or 1.48 volts for each of those. 1.48, 1.48. And when you're doing these for homework, try to draw large diagrams. I don't need to see every little calculation, but try to draw big enough diagrams where you can fit all these numbers in as you work through these, and anticipate that you're going to have to put these numbers on the diagram, so leave space for them. All right, so they have the same voltage, the 6 and the 12, so I can calculate the current through each of those. I'm going to use V equals IR once again off to the side, where V is 1.48 equals I times the resistance, either 6 or 12. I'm going to calculate those, and I get 0.25 amps of current for the 6 ohm resistor, 0.25 amps, and I get 0.12 amps of current in the 12 ohm resistor. If you add those two numbers I just wrote down, the two red numbers there at the top, up there by that 6 and 12 ohm resistor, the sum is 0.37 amps, which is the total current that was split at point A between those two resistors, comes back together at point B, and then flows through the 2 ohm resistor. So everything's consistent so far, and now I would like to calculate off to the side the power of my 6 ohm resistor. I'll just do I squared R, 0.25 squared times 6, which is 0.38, or just 0.4 watts. And the power of the 12 ohm resistor, which will be 0.12 squared times 12, that's 0.17, 0.2 watts. The reason I'm doing all this consistently to the tenths place is because what I want to look at is, in this particular circuit, I have a total of 7 resistors. And I want to find the total power for all 7. These 4 resistors, the 3, the 2, the 6, and the 12, which are actual resistors, if I add those powers together, I get 2.5 watts. Now on the other page, or your page, I also have the 1 ohm resistor, the power of the 1 ohm resistor, which was 1.2 watts, the 4 ohm resistor, which was 4.8 watts, previously computed, and the 0.5 ohm resistor, 0.6 watts. If I add those 3 numbers together, that's the other 3, so I have a total of 7 resistors. That would be 6.6 watts for those 3. So if I add up all 7, so we get the 3 at a 6.6 plus the 2.5 watts for the other 4, they have a small wattage because they have very low current out there. That becomes 9.1 watts of total power used individually by all the resistors added together. Now, that's a good number because if you look back at the other page, for when we had our simplified circuit for the total battery of 8 volts with this simplified circuit of 7.5 ohms, that also came out to be 9.1 watts of power delivered. So that checks out. It should check out because the power supplied by the battery should then be accounted for by the individual powers of each resistor within the circuit. Technically, the battery is supplying a positive energy or power, and the resistors basically are turning it into heat or light So that'd be a negative. And it's really a validation of the conservation of energy principle as well. The energy given, power given, energy per unit of time equals the energy used per unit of time. So it all checks out here, 9.1 watts.